Hello, I'm Shaden Alshammari, and today I'll be giving you an overview of our work on class-imbalanced learning using Bilevel-Optimized with Decay. First, data imbalance is very common in the real world. For example, here I have two real-world datasets. The first one is a large-scale image datasets for places classification. If we sort the class index according to the class frequency, we get the first plot. We can see that there are common classes with thousands of images, such as home images, and rare classes with 10 images, such as museums. The second plot is a species dataset with imbalanced classes as well. Many other datasets exhibit imbalanced distribution naturally. High recognition accuracy on rare classes is often crucial in various real-world applications, such as autonomous driving and cancer cell recognition, where more than 99% of the tests are negative, as shown in the plot. However, if we train a machine learning model naively, it will perform well on common classes, which are to the left of the figure, but poorly on rare classes. This motivates the well-studied class-imbalanced learning, CIL, which trains the model over class-imbalanced training dataset, but evaluates the classification accuracy over classes balanced testing dataset. Many solutions for the class-imbalanced learning problem modifies the training data to make it more class-balanced. For example, one way is to add synthetic examples to the rare classes. Another way to balance training data is data resampling, which undersamples common classes or oversamples rare classes. Another idea is emphasizing rare classes in the loss function by giving them larger weights. For our work, we started by taking a deep learning model and train it naively on the imbalanced CFAR 100 dataset. Then we focused on the classification layer, which is the last layer of the network. We noted that the norms of the classifier weights are skewed towards common classes, as shown in the plot. This motivates us to balance the network weights by regularizing their norms. Therefore, we started by using the common method with Decay, which is also known as the L2 norm penalty. Here, we start by training a model with no weight decay at all. Then, we add a weight decay with the hyperparameter 0.0001. We can see that the validation accuracy is getting higher. We increase the lambda further, which is the hyperparameter. And we can see that the validation accuracy is getting higher as we increase the lambda. And here we have a notable increase. Then, when we increase it further, the validation accuracy decreases. So we were at the peak. From here, we note that tuning with decay notably improves the performance. It raises the performance from 38% to 46%. However, hand-tuning with decay requires much manual effort. Therefore, we want to automate it. And we proposed this algorithm, which we called a population-based bilevel optimization. In this algorithm, we start with a population of k different models with k different hyperparameters. Then we train them for a period of time, and we evaluate them on the validation dataset. After that, we select the best performing model, which we can call the winning model, and reinitialize all of the other models to the winning model parameters. And we repeat the process of training and selecting the winning model and reinitialize the weights again. And we keep repeating this process until the end of the training. Another thing that our algorithm do differently is that we don't use a single lambda or a single weight decay hyperparameter for the whole network. Instead, we use a single lambda for each layer. This allows us to implement a pair layer with decay. In this table, we benchmark our method, highlighted by gray, by comparing it to existing CIL's methods. Combining our algorithm with other methods yields to the state-of-the-art performance, which is 51%. And here, we can see the pair class accuracy for our model, which is colored in blue, compared to the naive model, which is colored in green. We achieved higher accuracy in almost all of the classes. In future, we are motivated to explore regularization on pair filter weights rather than pair class weights. Finally, I would like to thank my mentors, Dr. Shu, Dr. Yusheng, and Dr. Diva, for their continuous help and support. And I would like to thank the risk community and my sponsor, KGSP, for making it possible for me to have this opportunity.